Sorry for the delay, guys. Your videos will come up probably on Tuesday because I accidentally recorded the first video on slow-mo, which means it was a 60-minute video, and even though I took off slow motion, it still decided to upload a 60-minute video worth of information because it didn't know any better, and that took 12 hours. So here we go with part 2, half a day later. So a car dealership has 5 red cars, 12 black cars, 8 silver cars, 4 blue cars, and 1 white car. They're going to put 8 cars out front on display. Let's start with the probability they choose 3 red and 5 black cars. Okay, so this is about subgroups. They can want to know about red and black, but they don't care about anything else. So first thing I'm going to do is count how many cars there are. 5 plus 12 plus 8 plus 4 plus 1 is 30 total cars. So that's going to be my denominator. I know I'm picking 8 of them, so I know I'm going to have 30 choose 8 in the denominator. Now, I'm picking 3 red cars. How many are there total? 5. So 5, choose 3. 5 black cars. So 12, choose 5. Now everything else, every other kind of car goes in its own group. You don't have to separate them by color because we don't actually care what the other car colors are. Granted, there are no other cars picked out of this group of 8 because we assigned them all colors. But of the other, it looks like 13 cars, we're choosing 0. Still good practice to put this in here for later. Okay, so 5 choose 3 times 12 choose 5 times 13 choose 0. And you're like, okay, get my handy dandy calculator or Google. And Google knows how to make this work, and this ends up being around to 4 decimal places, 0.0014. Not that great of a chance because we avoided every silver, blue, and white car, and we got 3 red cards out of 5, which is a large amount for 8. So it's pretty unlikely for this to happen. So let's try again. The next problem, find the probability that they choose 2 red, 3 black, and 3 silver cars. So again, same idea, 5 choose 2 red cars. Black, we chose only 3. Now, there were 8 silver cars, and we're also choosing 3 of those. That leaves out only blue and white, so there are 5 more blue and white cars that we're picking 0 of. This is still divided by the same total. So we do this in the calculator. Let's choose 3. And you'll notice that our chances actually go up. This is 0.0210. Which is over 10, it's about 15 times more likely than the previous one. That's because this 2 red, 3 black, and 3 silver represent a more natural pick of our population because they're the 3 most popular colors, and the 2 most popular colors got the most cars. Even so, it's only like a 2% chance of happening, so not that great, but certainly much better than a 14 out of 10,000 chance of happening. Now, here, in those first 2 problems, all 8 cars were assigned. What happens if all 8 cars aren't assigned, like in part C? Find the probability they choose exactly 6 black cars. So we know of the 12 black cars, 6 have to be picked. And we know we're dividing by 30, choose 8 still. However, they didn't tell us anything else, which means the other 2 cars out of the 8, since we're picking 8 and we know 6 are black, can be any color. That means every other color needs to be grouped together, just like blue and white were grouped together here, and just like silver, blue, and white were grouped here. Every color that's not black needs to be grouped together. There are 18 total of those, because the first 2 numbers, again, add to 30. And we're picking 2 of them. any two out of those, we don't care. But it sometimes simplifies, but you need to make sure to account for it or you'll miss it. So we have 12, choose 6, times 18, choose 2, divided by 30, choose 8, which is also 0.0242 if rounding. So a little bit more likely to get 6 black cars than our previous one. Still not great odds. And this can be extended to the last problem as well. The idea, 3 black and 2 silver cars, that's 5 total colors taken. That means the other 3 are our choice. Well, not our choice, it can be anything besides black and silver. So we have 12 black cars, we're choosing 3 of them. We have 8 silver cars, we're choosing 2 of them. Now of the other 10 cards, the red, the blue, and the white, we need to choose 3 because we picked 8 cars. Over 30, choose 8. So again, this goes back to the subgroups from the previous video. Break your subgroups down. If they ask for something specific, it's going to get its own group. Anything left over just gets paired together. So just be aware of that. So 12, choose 3, times 8, choose 2, times 10, choose 3. All divided by 30, choose 8. And this one, it actually has a pretty high probability. Because the less specific you are, the tends to be the more likely you are to get it. If I said, what are your chances of choosing 8 cars of any color out of the 8 cars you choose? Well, yeah, that's not a very specific thing. So of course you're able to do it at a high probability, in that case, a probability of 1. Now we'll talk only a little bit about page 4. The birthday conundrum problem, you can read about it. But generally speaking, if you want to know the chances of a room of a certain number of people, what are the chances none of them have the same birthday? It's 1 minus 365, choose n, not really choose, 365 permute n, over 365 to the nth power. The reason for that is, if you're the first person in the room, what are the chances you don't have the same birthday as anyone who came before you? Well, 365 out of 365. There are no days taken. You can hit any of them. So anyone after that has to dodge a day because you picked your birthday. So the next person has to dodge 1 birthday, and then 2 and 3 and so on. And it ends up simplifying to this formula. So if you want to know in a room full of 25 people, what are the chances that none of them have the same birthday? It's 1 minus 365 permute 25 people over 365 to the 25th power. So let's put that in the calculator. Okay, so you get this part of the equation ends up being 0.569 when you round to 3 decimal places. So 1 minus 0.569 is 0.431. What does that actually mean? Well, let's think about that. That means if you have 25 people in a room, there's only a 43% chance that none of them have the same birthday. And you're like, how is that possible? There are 365 days, and yet with only 25 people, you have a greater than 50% chance that 2 of them have the same birthday. It's one of those things that's kind of crazy to people. And they don't think that that can actually, it shouldn't take that much. But when you think about it, let's just talk about, let's say there were already 36 people in the room. That means roughly 10% of the birthdays were already taken. That means every additional person after that would have only a 90% chance of avoiding everyone else's birthday. And if you stack a bunch of 90% chances on each other, the chances that you're going to miss one, it doesn't take very long. So that's an interesting little fact about birthdays, and this is the last notes we'll do. I'm going to go ahead and update that 9.4 is not the homework. I'll take it out. And it's been fun. I will give you exam information on Wednesday.